from the highest energies, gamma ray down here, all the way to radio. Here we have our own Milky Way in the optical light. You see nicely the dust lanes. Then if you go to the infrared, for example, where dust doesn't play a role anymore, you see a lot of the older stars, which are very bright in the infrared. So we can do this, but there's one problem with this approach. This we can only do for the Milky Way and a few others. And the question is, are these objects maybe special? They all reside in a similar environment. And environment plays a role for the evolution of the galaxy. So we don't know exactly if these are similar. So we can use a different approach, and that's in situ, meaning we observe many objects at many different times, and then we derive average parameter of these objects at these times and try to describe the evolution that way. Here, for example, we have this diagram shows 300 galaxies in the cosmos field, which is a relatively large field observed at the northern sky, observed by the infrared satellite Herschel. And it tells us a lot about the evolution of these galaxies, but we have to derive average parameters for these classes. So now the question here is, or the problem is, we only have or get statistical parameters, average parameters. Question is, how well do these average results describe a very specific object in our side? So you have pros and cons on both sides. This can only be done for a very limited number of objects. This can be done for lots of objects, but gives only a more limited view on what happens. So, now, nonetheless, if you study the High Redshift Universe, you have no other choice than using large samples of galaxies. And here is an image of the very famous Hubble Ultra Deep Field. It's one of the deepest observations on the sky, done with a wide array of filter bands with the Hubble Space Telescope. So it gives us the best spatial resolution on the sky. And if you look, each of these points in here is a galaxy. And we have just by looking on them, we cannot tell where they are and what they are. So and it's almost impossible. Here also you see nicely the variety of objects you find in these images. But it's almost impossible to go and get spectra which would give us much more detailed information about them for each object. So we have to cut down on classes of galaxies which we are interested in to answer our questions. And that is what we do before we go and do spectroscopic observations. We select objects and we try to use properties of these objects which tell us already a little bit about where they are. For example, we can select so-called extremely red objects. These are very dusty starbursts, meaning they produce a lot of stars in one moment. And the dust is reddening these objects. Another subclass of these EROs are also passively evolving. That means these galaxies do not form new stars anymore. They just sit there and these stars age. That's why they get red. Another way would be to look for what we call distant red galaxies, very massive galaxies with 10 to the 11 to 10 to the 12 solar masses in stars. Also starburst galaxies. They have high star formation rates with 100 solar masses per year. In comparison, our own galaxy only produces a few stars per year. Sub-millimeter galaxies, another class, and then planet alpha absorbers, which can be identified by the absorption of ultraviolet light. And what we use to select these galaxies are these diagrams over here, called color magnitudes or color diagrams. That's where a color for an object in astronomy is the difference between the flux in two different filter bands. By definition, it's always the blue filter band minus the red. And that gives us an idea of what these, or a basic idea of what these objects are made of. And different classes of objects have different locations in these diagrams, and that can be what we can use to pre-select them. And we can measure these magnitudes and colors from images. by measuring the flux of these objects. So a very nice way of cutting down on. But the maybe most successful method to actually select high redshift galaxies is the so-called Lyman break method. It selects galaxies which show a break in the spectrum. Here we see the wavelengths versus an arbitrary flux, and you see how the spectrum of this object here breaks down at what would be a laboratory wavelength of 912 angstrom. And this high flux here, that comes due to strong star formation in these galaxies, so they produce a lot of ultraviolet light. This 912 angstrom is far into the ultraviolet light. And then we have, within the galaxies, we have a lot of gas and dust, and also within or between the galaxy and us as observers, there's also a lot of gas. This gas absorbs these UV photons. So everything which has more energy than energy which is relates to wavelengths than the 912 angstrom photons. So everything which is left here gets absorbed on the way from the galaxy to us. And we see this break. And that can be used to select these classes by galaxy. And by knowing where that is, we actually can make a first estimation of the distance. And the technique we use for this is the so-called Dropout Technique. Here you see one of the examples from one of our work. These objects, this object here is observed in many different filter bands. You see them, comparable set of filters listed here. And we cut out little sections out of the spectrum, and that gives us some information about it. But if we look here in the ultraviolet range, which is observed by a satellite called Galaxy, we see that object is not there. And it should be there if it is not at its certain redshift. But here in the U band, which can be observed on the ground, all of a sudden that object pops up. So that's what we call a dropout technique. And we can use these images to search for those objects which are within in a redder filter band, but not in a blue. And this method is actually ideal for targeting the highest redshift galaxies. Here we see examples for galaxies which have been discovered at redshift greater than 9. That means the universe was just a few 100 million years old. And you see here that is a composite of all optical wavelengths, and then you go in the near infrared and in the mid-infrared regime. And here we go from a redshift around 9. Here we have a redshift 10 sample, and that's almost 11. You see how this object pops out here in this near-infrared filter band, and all of a sudden that moves further to the next one. So the higher it's redshifted, the further into the red that detection filter moves. So very elegant method to detect these objects. The record holder today is a galaxy at a redshift of 11.9, detected by a group around Richard Ellis, and that is at an age about 400 million years after the Big Bang. Here down we see plotted the very low resolution spectrum, so the flux from these images versus the wavelengths, the central wavelengths of the filter used, and then it is compared to theoretical spectra of a galaxy, and it nicely shows the break and gives a high probability that is shown here that this object resides at a redshift of 11.9. Now, hunting for the highest redshift object is not just nice to have it, it immediately gives us information about the evolution of the universe. If I go back to this picture from the beginning, because what it does, it pushes the limits for this transition here, from the dark ages where the universe was completely neutral to where the first stars have formed and started to emit light. We still don't know exactly where that is. So with every galaxy we can detect at a greater distance, we know that limit is pushed further back in time. So we are right now at about 400 million years. But who knows, maybe in a year or two we go even closer to the Big So the first sliver of information now. So what do we know about these high redshift galaxies? At redshifts greater than 9, this is where we have the most distant star formation going on, and is where we think the epoch of what we call reionization. So the first stars are formed due to density fluctuations, so the medium is not smooth. You have these little pockets of higher density, which all of a sudden attract more matter, and the material starts to gravitate towards those denser areas and starts to become clouds and collapse into stars. That's what we emits light and starts to reionize the universe, and that's what we call epoch of reionization. Then we go a little bit closer to home, redshifts of 5 to 6, that we have very young objects there, about 100 million years old. Masses are relatively low, only 10 to the 9 solar masses. They make about 1% of the local mass density, so it's about 1% in these galaxies. They are very compact galaxies with relatively high star formation rates of 40 solar masses per year. At a redshift of 3, that's when the universe is about 2 to 3 billion years old. These objects have grown in size. They are 10 times more massive. They host a large part of the star formation.